Today we are going to discuss the separation axioms of topology. What is a T0 space C? Let X tau be a topological space. Okay. Now, when will this be called a T0 space? C, if for any pair of distinct points, say X and Y, okay, there exists an open set such that either it contains one point X or Y. Okay. That means, suppose this is X, this is small x, this is small y. Now, when will the space be called T0 space? If for any x and any y such that x and y are distinct, different points, then I need to get one open set, at least one open set, which contains either x but not y, or which contains y but not x. Means either this I can say, or this. Okay. So what can be an example of a T0 space? See, let X be consisting of those points A, B, C, and let me define tau as Y, X, A, C, A, C. Okay. Is this a topological space? You can easily verify that yes, this is indeed a topological space. Now, is this a T0 space? Let us check. If I take A and C, okay, I am getting the singleton open set A which does not contain C, right? Similarly for C as well, here the singleton open set which contains C is there, but it does not contain A, isn't it so? Now, what do I need to do? I need to check for AB and BC. I have already checked for AC. Okay, so see, this contains A but does not contain B. Okay, and again if I check for BC, then this singleton C is an open set which contains C but does not contain what? B. Okay, so what can I say? That yes, this is indeed an example of a T0 space. So now let me come to the definition of T1 space. T1 space is saying that X tau be a topological space if for any pair of distinct points X and Y in X, there should exist two open sets. Okay. There exists two open sets, say u1 and u2, such that x is belonging to u1 but y is not belonging to u1, and this all will be replaced by and y will be belonging to u2 but x will not be belonging to u2. So what is the idea of a T1 space? See, let this be our x, the space. Let this be small x and let this be y. For any two distinct points, x and y, what should we get? We should get two open sets such that each open set contains exactly one. Exactly one. That means here, suppose this is u1 and suppose this is what? u2. As you can see, u1 is containing x but is not containing y, and u2 is containing y but is not containing what? X. Here u1 and u2 need not be disjoint. It is possible that they have some elements in common. So this will be called what? This will be a T1 space. Now you notice one thing, that every T1 space is what? A T0 space. Okay. Why? Because see here the OR is replaced by AND. So T1 condition is stronger than T0 condition, and by default every T1 space is already a T0 space. Now, is this a T1 space? This was a T0 space, right? But will this be a T1 space? Let us check. For any two pairs, for A and C, we already checked that yes, this is containing A but not C, this is containing C but not. And what about the other pairs? That means AB and BC. Are we getting any such open sets? See, this open set AC, this is containing A but not containing what? B. Okay. Also, this is containing C but not containing B. Is there any open set which contains B but not A or not C? No, because the only open set which contains B is X, and X has all other points as well. So no, this is not a T1 space. Okay. X tau is not T1 in this case. Okay. So what do I need to do if I want to get a T1 space? Let me extend this, okay? Let me extend the topology and let the new topology be okay. So what I did, I took the discrete topology. Now let me see if this is a T1 space or not. Okay. Now A and C we have already checked. What about B and C? This contains C but not B. This contains B but not C. And what about A and B? This contains A but not B. This contains B but not A. So for any pair of distinct points, we have got at least two open sets which satisfy the condition. So in this case, this has become a T1 space. In this case, X tau is a T1 space. Okay. So now let us check what is T2. Let X tau be a topological space if for any pair of distinct points x, y belongs to x, there exists two open sets u1, u2 belongs to tau, such that x belongs to u1 but y does not belong to u1, and y belongs to u2 but x does not belongs to u2. Till here, the condition for T1 is exactly the same, but here there is one more condition, and that is the two open sets should be disjoint. Okay, the two open sets should be disjoint. So what will this picture look like? See, these two are what? Disjoint in this case. Okay. So what is basically a T2 space? A topological space where for any pair of distinct points, I get at least two disjoint open sets which contains exactly one of the points. As you can observe, T2 space is always T1 space. Why? Because here just one more condition is added, and that is the disjoint property. Okay. Now, is this T2? Is this T2? Let us check. For A and C, this contains A but not C, and this contains C but not A. And you see that both are disjoint, right? This singleton A and singleton C are both disjoint as well. Again, for singleton A and singleton B, this contains A but not B, this contains B but not A, and they are disjoint as well. Again, for BC also. Okay. So, can we say that this is a T2 space? Yes, this is a T2 space. In fact, you can prove that a discrete topological space is always a T2 space. Okay. So, this is a good exercise which you should try. As I said, every T2 space is T1 space, and every T1 space is what? T0 space. However, you must be careful because the converse is not true. Every T0 space need not be T1, and every T1 space need not be T2. Alright,